Important consideration of data collection and curation for reliable benchmarking of end-user eye tracking systems. My name is Iakov Chernyak. Our goal was to build a benchmark that has a number of characteristics which we believe are lacking in many benchmarks in the literature. At first, the benchmark has to be reproducible. Even for the same eye tracker, different research groups and their papers report different results. That is due to the difference in data collection environments, which are often difficult to reproduce. The benchmark has to be comparable. We want to be able to assess different eye trackers and be able to compare results. And we want the benchmark to be representable of practical eye tracker usage, instead of showing the best case only. In order to achieve these goals, we propose to shift the paradigm of what use case that benchmark aims to estimate. We split the target audience into two use cases, where the first is operator-assisted eye tracking, and the second is end-user eye tracking. The example usage of operator-assisted eye tracking is marketing research, which allows data to be recorded, allows gaze, post-processing and filtering, and allows a wide range of restrictions to data collection. End-user eye tracking examples usage includes keyboard typing, UI operation, aiming to enemies in games, and any other kind of potentially interactive eye tracking application. The major difference here is that we impose no restrictions who can be the end user, and we minimize parameters that can bias the result. Most of the benchmarks in the literature are geared towards operator-assisted use case. It's good when you need to know how the tracker behaves for a narrow group of people with a restricted eye tracking setup. The benchmark would represent the maximum capability of the eye tracker, which can be achieved under certain relatively narrow conditions. Such approach has a number of cons with respect to the previously described factors. Operator-assisted eye tracking often has participant preselection, which has different subjective rules and which can be hard to reproduce. Participant preselection can lead to the benchmark that only represent people with eye shapes, cornea shapes, and other features that yield high accuracy of eye tracking results, which will be achievable only for those people. Such a result might have some applications, but it's not representative of general public. Operator-assisted eye tracking assumes the presence of operator which verifies the eye tracking quality. For example, sometimes an operator might request multiple recalibration until the best quality can be achieved. This allows multiple recalibration iterations, where theoretically sooner or later even random calibration coefficients would converge to a reasonable result. That would bias the result and make them very operator dependent. The more restriction we impose on the data collection environment, the more additional parameters we introduce that can vary from one research group to another. Often operator-assisted eye tracking benchmarks utilize filtering, which filter out bad eye tracking results on purpose. This is reasonable for certain research environments, where the accuracy of the data takes priority over integrity and continuity. The downside of this is in reduction in comparability and representativeness. For end-user eye tracking, we have no participant preselection, minimum operator influence, and as few restrictions to the environment as possible. It will represent general-purpose eye tracking usage for end users. Still, for some laboratory environments, it might be less representative compared to operator-assisted eye tracking. Next, I want to introduce some important features for data collection. Just like in any other data collection for eye tracking and benchmarking, we suggest to collect information about every participant. It includes information about the presence of eyeglasses, contact lens, covered lens, what eye color, skin color, makeup the participant has, and whether any conditioner or surgeries of the subject. This data can potentially bias the result, but we can do nothing to mitigate that, other than just collecting such information and later using that to analyze how each factor affected the result. We have to ensure uniformity of the target point distribution that were presented to participants. The way how uniformity was achieved has to be explicitly described in the benchmark, since it can affect the results. Participants decide by themselves the timing when they are looking at the displayed target point. The gaze sample from that moment should be used, because it more closely approximates when user would press a button when using an eye tracking based user interface. Calibration should be done blindly. That means that during data collection, the operator has no way to confirm data quality, or even to know whether calibration was successful or not. Randomized background brightness. Dark backgrounds should be well represented in the datasets, since it will cause people to dilate, and dilated people has different people center. This causes additional challenges for eye trackers, and that should be well represented. Include headset drift. Generally, we allow participants to remount or adjust the VR headset anytime they feel need to, since the end user may also do so. In addition, the benchmark may optionally include the data regarding the eye tracking performance after compulsory headset remounting. Since the operator has limited control during the data collection, there is no guarantee that participants is looking at the target when pressing a button. In fact, we observed many cases when participants could not find the target because it was out of field of view, but the participant mistakenly pressed the button as if they were looking at it. We will refer such mistakes as participant mistakes. Such mistakes bias the benchmark results and have to be detected and removed from the dataset. Besides the participant mistakes, the eye tracker can also be a source of the observed inaccuracy spikes, such as when image processing fails. We will refer those as eye tracker mistakes. We found that many research groups designed data filtration in order to filter out both participant mistakes and eye tracker mistakes. Some example of such curation would be omit entire fixation point if the estimated case during the fixation has standard deviation more than XX, or omit the entire fixation point if the tracker reported failure on more than XX% of frames, or omit the entire fixation point if its angular distance to the ground truth is bigger than some small threshold. This leads to a final assessment that would be achievable only under ideal situations. Moreover, by varying coefficients XX, we could get nearly any results for estimated eye tracker characteristics. However, such results would not take place in practical eye tracker usage. So instead, we proposed in the paper different methodologies that are designed to filter out only participant mistakes and try to avoid filtering eye tracking failures. For example, we filter out fixation point only if there is not even one frame of successful eye tracking output. And we filter out fixation point only if the angular distance to the ground truth is way too big even for the frames where eye tracker has failed image processing. In our paper, we also discuss how to pick the appropriate coefficient XX in order to filter out participant mistakes and minimize the filtering eye tracker mistakes. This is an accuracy benchmark result for the FOV0 headset. Here, each vertical bar represents an individual participant's mean angular error. There are a total of 157 participants in this benchmark. We performed an ascending sort of bars so we can see the range of how eye tracking accuracy varies from person to person. From this figure, we can see that mean accuracy is about 1.1 degrees. We also can see the rate of people who had some difficulties with eye tracking due to presence of contact lenses, wet headset fitting, eye conditions, or any other miscellaneous problems. Please read the paper to learn more details on the FOV0 benchmark. There you can read about statistics on participants, data collection procedures, and curation methods. You can also download the raw data from Github, which can be used to reproduce the result of our benchmark, or test other data processing approaches to see how they impact the results. Thank you.